Hi everyone, welcome back. So in this video, we'll showcase how to create a circuit model for our advanced PCell here. And this is very useful because it allows us to leverage the fact that IPKISS can simulate S parameters and circuit transmissions right within Python. And we won't have to kind of dance between a numerical simulation or make the numerical simulation run every time we want to see it. We can actually export the results and come back to it later. So what we'll have to do first is we'll have to add a new class, and then next we'll also have to extend part of our simulation so that it exports this S parameter. So first off, let's do the extension of the simulation first. So up here in outputs, we can have our simulation object here actually create something for us, whether it's a variable or if it's a file. So what we want to do is we want to get the S parameter file. So how to do so is in outputs, we can add a i3.deviceSim, and there is a function called macro output. So this macro is for the output section, and it requires first a name. So what we'll do is we'll call it macro get S param, and this name is very important, so we'll keep note of it in a bit. And then next we'll provide a file path, which is what this macro will output to. So the file path will be a file called cdc sparam.s4p. So an output file must be provided for this function. This is one of the necessary parts of this function. And we'll want to create a S parameter file. And this S parameter file will be in the S4P format, which is compatible with both IPKISS and numerical interconnect. So once we have that now, remember the comma here, we can now give it the commands in the same way that the macro function we did in the last video down here can be called. So here we'll have the commands, and then in this command we can be more explicit with our LSF process. So we'll want it to run the simulation that we set up already. After it runs, we want it to do the EME propagate. So let me copy over so I don't do any incorrect typing and have to debug. So we'll type that here. So we'll do an EME propagate. So if I still have my setup open here, basically you click run, and then there'll be a EME propagate button at the bottom for the EME solver. Let me see if I can showcase it real quick. So why don't I make a delete. So once you run an EME simulation, at the very bottom will be an EME propagate. That's what we're going to call here. And then once we have that, we'll ask the macro to do a EME analysis. So we're going to do a wavelength sweep. So what we want to do is we want to enable the wavelength sweep. So that's what the first line will be. We set up the correct start and stop wavelengths, and we set up the correct number of wavelength points. Then we do the sweep. And then we'll want to export the file after. So that's what the subsequent lines are. So we'll first do a wavelength sweep. We enable the wavelength sweep. We then set the start and stop wavelengths. We then set the number of wavelength points. And then we we ask it to do a EME sweep, which is the wavelength sweep. Now that the sweep is complete, we have our results. So we can ask it to export the results. So export EME sweep into both S parameter .s4p, which is a touchstone format, or the .dat format for numerical, just so we can keep it kind of in the proprietary format if necessary. And that's all you really need here to make sure it exports the S parameter. And this is the same as running the wavelength sweep and then clicking export here, choosing your file, and then mapping your ports to the S matrix. You'll notice that I didn't have to map the ports to the S matrix explicitly, and the reasoning is because in our code from a few videos back, we set up our port naming to be the correct things, so we don't have to do this step. So next we'll go to the very bottom here, and if you recall, we had a simulation get result function that we forgot about. So here we can ask it to execute our macro s_param like that. And then so now if we run it, the whole thing will run and it'll generate our s-parameter data. So we'll let it run here, and you'll see I already have it here in our folder on the left, but we can let it run and confirm that the code is working properly. So here it's making our simulation automatically. We asked it to inspect, that's why that window showed up. Otherwise, it'll only run once and then export the results. So here's our inspect, we close it, and then now it'll do the actual sweep. So here's our sweep happening. It ran EME, and now it ran the wavelength sweep, and then now it exported the data. So now we have our s-parameter data here, and everything's working correctly now. So what we want to do next is we want to connect these s-parameter files to this PCell so that if we make a circuit, for example, we can call these results directly. So I'm going to disable this code here because we don't need it anymore, and then we'll just leave a note here called simulation in case we want to go back to it at some point. And then what we want to do next is to connect the s-parameters. There is a class we can create, similar to how we created a layout class up here. Oh, sorry, it's over here. We create a layout class over here. We can do the same and create a class for the circuit model. And the naming is case sensitive, so make sure you have the correct naming. And then we can call IPKISS function for circuit model viewer, circuit model view. And then in it, we can specify a variable called touchstone file name. And then this can be set to a i3 string property. And then the default can be set to that file we just made called cdc s_param.s4p. And then you can also add a documentation if you want. So just say touchstone file and keep it simple. So with that, we have this file located. It has to be native to this script at the moment. So this cdc s_param.s4p has to be right next to contradirectional coupler.py. If it's not, it could pop an error. But yeah, this is kind of the limitation with how we implemented it here, but you can change up the implementation how you wish. But next what we need to do is we need to create a function for generate model. And this function will be the one that returns the value, and we can map our S parameters to our ports. So we can create a variable called smat for S matrix, and then it is a i3 circuit sim. And then in circuit sim, there is a function called S matrix 1D sweep. And then we'll say from touchstone. So we load the touchstone file. And then here we can give it the touchstone file. So self touchstone file name, and now it's connected. And then next we need to map the nodes. So we'll do a mode map, and then squiggly brackets here for dictionary. And then we'll set port 1 to the first mode, and then part of port, so the actual output S parameter port 0. And then we'll just repeat that for the next 3 ports. So they're all going to be mode 0 because we only did a single mode simulation here. And then we'll map our port 2, 3, 4. And then they should line up with the S parameters port 0, 1, 2, 3. And with that, that is done. So we can now create a model object, i3.circuitSim again, and then we'll do a B-spline model, and then we'll get our S matrix. So from S matrix, we give it our object, and then we just do a spline basically to make the transmission look smoother, and then we'll return the model. So it interpolates a bit. And with that, we're good to go. So we can also, and yes, we also can add in, for completeness, a netlist class. So i3.netlist from layout, just in case we ever want to export a netlist. So with that there, what we can finally do now is in our script down here, we can try to read out the S parameter transmission. So let me see what this error is. Okay, the error is not important. So what we can do now is, let's say we want to see the transmission from S parameter. Oops, S parameter. We'll create a CDC object, and it'll be a contra DC, which is our class. And then we'll create a circuit model. So CDC CM will be a contra DC. Sorry, we can just do a CDC dot circuit model. So we're not declaring it twice. And then what we can do is we're going to import NumPy because we're going to need it to visualize some stuff. To input a wavelength range, just to make things fast and easy. So a wavelength range will be wavelengths, and then we'll call it np.linspace. We'll set it to 1.5 to 1.6 microns with 201 points. And next what we'll do is we'll create a object called S for S matrix, and it'll be CDC circuit model, and then we'll get S matrix, and then we'll also pass our wavelength over. So wavelengths equals wavelengths. Just name the variables the same just to keep it fast, and then we can visualize this circuit model. So we'll visualize, and then we can also name the pairs when it graphs itself. So we'll do term pairs. We pass a array to it, and in it we'll do, we want to see port 1 and to port 2, so basically 2-1, S21. And then we'll also want to see 3-1, so port 1 as the input and port 3 as the output. So we can label this like that. And that should be good enough that we can give it a shot. So what we are expecting to see is it should give us the transmission response that we saw in numerical EME previously, but now loaded from our S parameter. Sorry, I spelled linspace wrong. I wrote linscape space. There you go. And voila. So now we have our transmission response loaded from S parameter. And you can see that our port 1.3 and 1.2 are showing the transmission and throughput and drop put. You may notice that port 1 to port 2 is not showing the transmission, but rather the drop. And the reasoning is because there is a twist you have to do so that the waveguides don't overlap. And we'll showcase that in the next part, in part C, where we connect the contradirectional coupler to a Bragg grating and a bunch of waveguides to create a full circuit. And then we'll output the circuit model for that whole transmission there. But yeah, for now, thanks for watching. Take care.